Right, so we left off and we were dealing with the 4-to-1 mix. We gave the logic diagram. This is the logic diagram for a 4-to-1 mix. Something like this. One output, 4 inputs, data selectors. That is what it looks like. We wanted to find what is inside here. What is inside, how do you do that? You find the truth table. This one, I think it shows much more. I have my inputs here, my truth table. I have my selectors, their inputs as well. A0, S1, because I made a lot of assumptions and I'm realizing it might not be okay. I have only one output. So in this case, if I say my inputs are D0, D1, D2, and D3, it means here I have my inputs D0, D1, D2, and D3. But those inputs, they correspond to their data selectors. So if I have the selectors on 0, 0, my input will be D0. And etc., etc., etc. Now, what is my output? My output here, when the selector is D0, will be D0. Here it will be D1. Here it will be D2. Here it will be D3. All these outputs are ones. Or I can do this. Output 1, 1, 1, 1. Now, what is Y? Y is the sum of D0, S0 bar, S1 bar, plus D1, S0, S1 bar, S1, S0 bar, plus D2, plus D3. I think we are past that. To the logic diagram, you have, so we said Y is equals to D0, S1, D1, S1, D2, S1, D3, S1. This is nothing. It's like this. Plus. To the logic diagram, I said you have inputs D0, D1, D2, D3. Let me just do this. Then I also have my data selectors. As someone suggested, okay, there is my NOT gate. S1, there is my NOT gate. All right, so to get this first term here of my multiplexer, I have D0, right? As S0 bar, I have S1 bar. And the second term, I have D1, I have S0 bar, I have S1, and I do the same for D2, for D3. It means I have another end here, I'll have another end here. But there are these plus here. What does a plus mean? That's an OR gate. Yes, you can have a 4-input OR gate. It's possible. So I can have something like this. That is a 4-input OR gate. And my output will be Y. With 4 inputs, I can sum them up, get one output. How do I do that? I use a multiplexer. This is how you come up with the circuit, the logic circuit of a multiplexer. Here I have the logic diagram of the multiplexer. How do you come up with the circuit? Truth table, expression, circuit. It doesn't change. Designing. You have a problem, you need a solution. How do you get to the solution? Analysis. How do you analyze? In logic design, we analyze by finding the truth table, finding the expressions, minimization, then coming up with the logic circuit. From the logic circuit, you then go and design. You know, I need to put the gate here, I need to put the gate here. Then you design your solution. We also have a demix. We also talked of a demultiplexer. And with the demultiplexer, we have one input, many outputs. Hey, this is not okay. One input, many outputs. One input, or let me say n. Nope, not n. It's one input, many outputs. An example, there we have our this is a one input, four output demultiplexer with our selectors. So what this one does, for example, the Y that we had here, it is output here. It is a sum of all these four inputs. You have a system. I gave an example. You have a system, four inputs. You are inputting sound, you are inputting video, you are inputting internet data, you are inputting images. What the internet does for you, it takes all this and it moves as Y. Because you don't have to create a channel for this, a channel for this, a channel for everything. You can sum them up and use one channel. But at my recipient, I will need to separate this information Y in one channel. How do I separate it? I input it in my demultiplexer. So I have a demultiplexer. The demultiplexer does the job and gives me my four outputs. Now I have my sound here, I have my video here, blah, blah, blah. So this is my channel. I only need one channel instead of four channels because I have four inputs. This is basically how the multiplex and the demultiplexer functions. Not only in the example of the channel, many examples of application. Right, now the logic circuit. How do we come up with the logic circuit? One, a truth table. So for the truth table, I have my data selectors, the most important ones. Those are my inputs. They determine my outputs. What did I put here? So I have my outputs, D0, D1, D2, D3. When my data selector is like this, 1, 1. When it is 0, 0, I know my outputs, D0, D1, D2, D3. I know when it's 0, 0, I only have this as an output. The rest are zeros. I know when it's this, I have this, zeros. I have this, zeros. I have this. So when my data selector is like this, the output which corresponds to that is only D0. My data selector is this. The only output which corresponds to that input is D1. Now to the logic circuit. Now to the logic circuit, I have four outputs, two inputs. So here are my inputs, the data selectors. I have S1, S0. And this is S1 bar, and this is S0 bar. There is a NOT gate somewhere here. Very annoying to keep drawing. There's a NOT gate there. Well, let me do it. Someone will put a dot in the exam. Say you did the same thing. I will deny it, but it will be true. Voila. Not gate. All right. Before the logic circuit, we have the logic expressions, obviously. What is D0? We get D0 when, let's put our input here. There's another input Y. This one, we left this one, this input here. It has to be there. We have an input Y and the data selector. This is my DMix. Okay. Right, this is my DMix. I forgot an input. My input Y is 0, S1, and my output D3. So my truth table, it has an input Y, which is always 1, because you are always receiving information. When it's 0, you're not receiving anything. So you cannot output anything. It stays 1. What is D0? Sum of products. D0 is equals to Y, S0 bar, S1 bar. What is D1? D1 is equals to Y, S0, S1 bar. What is D2? This is D2 corresponding to this value. D2 is Y, S1, S0 bar. This is wrong. S0 bar. Nope. This is bar here. Vice versa. All right. What is D3? D3. This is D3 is equal to Y, S1, S0. You then go to draw your logic circuits. You then go and draw your logic circuit. So add my Y right here. So to get D0 is Y S0 bar S1 bar. And this is my D0. I do the same for D1, Y S0 S1 bar. I do the same for D2. I do the same for D3, etc., etc. My circuit is like this. Everything else is inside. This is what you design. But what is inside are all those gates. You only have outputs, inputs.
Jose,
Yes.
is it always but truth table hapo kuti ndo kufanira kunyora kuti S1 S0 kana ndoona ngonyora kuti S0 S1?
Yes, you can do that as well. Same difference. Same difference.
Okay.
Same. I think, but I advise you to do this. S0, S1. But even if you do this, it's the same difference. S1, S0. Because here it doesn't change the variables. They don't change. What changes are just the letters, symbols. Letters don't mean anything. If I say A is equals to 1, B is equals to 1, here it doesn't change. This can change. The numbers don't change. All right, we are done with combinational circuits. We are done with combinational circuits. The next thing we are going to be dealing with are sequential circuits. Sequential circuits. But before we go there, I think there's one last thing. Code converters. We didn't do code converters. Questions before we start code converters. Questions, comments, discuss. Zurubati.
We are following.
You are following.
Yes, sir.
We thank God for that. All right, let's talk code converters. All right, what is a code converter? Let's talk code converters. Where is my screen? at code converters. Right. We have different systems which run with the different codes. I think we have a number of codes. We have an gray code. We have an BCD. BCD, I think there's 8421. This is one I know mostly. We have an access 3 codes. Where this type of codes. You can have one system which runs on this code. You can have another system which runs on this code. We have also decimal here. But it doesn't mean since they are running on different codes, they should not communicate. If you want these two systems to communicate, you have to put something there, a code converter. So that a system which operates on gray can then function with a system which operates on XS+3 code. That is the function of the code converter. Two different systems, two systems using different codes. How do they then communicate? So the code converter is sort of a translator, two languages. You have a translator in between you. How do we deal with these code converters? I'll give an example. We have a 4-bit binary, 4-bit binary, gray code converter. How do you come up with the circuit which works as a code converter? How do you come up with the circuit? The problem is you need the translator, you need the code converter. Solution, analysis, truth table, canal maps, minimization, logic circuit, then you go and design. To begin with truth tables. So my code converter, what will happen with it? It's a 4-bit binary to gray code. It has 4 input bits, which are binary. It has 4 output bits, which are gray. Right? To my truth table, what do I have? Let's say my binary, I have A, B, C, D. This is binary. I have A prime. No, let's put capital letter A. A, B, C, D. This is gray. So I have my inputs on my left. I have my outputs on my right. For binary is very easy, etc., etc. 0, 0, 1, 1, 0, 0. Let's just 0, 1. Let's just end it here. It continues until we have 16. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. This is binary. Very simple. Now on this other side, the output will be gray. What does the gray code looks like? What does the gray code look like? It's 0, 1, 1, 0, 0. Here, 0, 1, 1, 0, 0, 1, 1, etc., etc. It's 0, 0, 1, 2, 3, 4, 0, 0, 1, 2, 3, 4. Then I have 0, 0, 4 zeros again, 1, 2, 3, 4, etc., etc. You need to know what the gray code looks like by now. For the B, I have 1, 2, 3, 4, 1, 2, 3, 4. I have 8 ones, 1, 2, 3, 4, etc., etc. There are another ones here. For the A's, there are 8, 1, 2, 3, 4, 5, 6, 7, 8. Then you have your ones continuing until you reach 16. I'm just too lazy to go all out until you have 16 outputs. This is my truth table. On one side, you have the binary representation. On the other side, you have the gray representation. And these are all corresponding, like this, like this, like this, etc. So what this means, if I input 00 in my system, I will get an output 00 gray. It doesn't change. For this one, it doesn't change as well. But the third one, look what happens. If I input 0010, the output will be 0011. What is it that make those changes? What makes those changes is the code converter. Now, if I am to fill up this whole table, I will then find maybe I'll use the K-map to find the minimized expressions for my outputs. What is A after my Carnot table? What is B after my Carnot table? What is C after my Carnot table? And what is D after my Carnot table? If you input the Carnot map there, you find out that D, where are we in Africa? I'm not going to do that. You are going to do that. I think I'll give this as an assignment. Too much work. Too much work. I'll give this one as an assignment to finish this one up. It will be assignment number 4. Yes, assignment number 4. A lot of assignments. Yes, yes. The thing is, my assignment what happens is I choose the best. And it is what it is. What did I want to write? The expressions will come up like this. Right. So I had A, B, C, D, A, B, C, D. I had A, B, C, D. What is A? A is equals to A. It doesn't change. What is B? B is equal to, let me see. Right. B is equals to 4 and 3, 4 and 3, A and B. A, B. After the Carnot maps. C, what is C? So C is 2. C is 3, 2. 3, 2. So it's B. Nope, what is happening? B, C. And D, for D, that is 1 is 2, 1. C, D. Right. There I have my solutions. After your truth table. Okay, this is not an assignment. You have the solutions already. After your K-map, you will find these solutions here. And with these solutions, you can then go on and construct your logic circuit. Your logic circuit, we have 4 inputs, A, B, C, D. In binary. The outputs will be A, B, C, D in gray. Now what is A? A is equals to A, it doesn't change. What is B? B is equals to A and B exclusive OR. Exclusive OR. Nope. Exclusive OR, it looks like this. All right. What is C? C is B exclusive OR C. For practice sake, go through the truth table yourself with all those 16 variables. Learn how to write the gray code. So we also have C and D. Another exclusive OR. Like this. So this is a code converter. After the design, it will be like this. 4 inputs, which are binary. 4 outputs, which are gray. And these exclusive gates are doing the code conversions. Very simple stuff. This is where the key is. Truth table, logic expressions. How do you come up with logic expressions like this? Minimization. How do you minimize K-map, Q method, whatever you choose? Believe me, K-map is not that complicated. So the things we've been doing from the start, now you are applying them to make code converters, to make multiplexers, etc., etc. Questions, comments before we start another session? Fresh one with sequential circuits, sequential machine fundamentals. Questions and comments? Okay. None. Questions and comments concerning the course so far? 52. Feedback. Well, I think tine minutes bicha until the 40-minute limit. Let's utilize them. All right, 10 minutes.
Assignment ya matiba irudi waringa.
All right, assignment and also assignment. The third practice. Practice. Because I'm too lazy to go to 16 variables, repeating the same things we've been doing, all those zeros and ones. I'm too lazy. You, however, should not be lazy. You are supposed to practice. Because the thing is, I'm probably lazy because it's in the exam. So, well, it is what it is. Comments, feedback on the course. Yes.
Saka tutoona wapedza zvarini course like
within I think by next week I'll be done.
All right.
Let me just say, Papa, for the face-to-face lectures, I'll be done with the course.
So nyora exam je.
Voila.
All right.
Comments, feedback. Don't go out already. Why I think I want to go and roll everything I'm going to tell right. Nope. Right. This one is done.
Writing board,
But that is a lie.
one.
Oh, but board why? I don't know what happened. No, we are done here. We join soon after. Auntie? Yes, another question.
Hakuna kana tuma exam inse.
Tuma?
Exam means.
And I just gave you a hint. Is about less than 5 minutes ago. I gave you a hint.
Oh,
believe me.
I
gave you a hint.
in the bad.
Go through the rest of the videos. You see those hints. We are done.